So today's goal is we're going to wrap up mass flow, and then we're going to start NP completeness, which is the next big section. So with NP completeness, we are kind of entering the realm of hard problems, right? And maybe you've heard of this term NP completeness. So far what we've done is like all tractable polynomial type problems, right? Kind of some algorithms are more complicated, maybe dynamic programming. Max flow algorithms are a bit more subtle, but still they're polynomial and solvable. So now we are going to see that the real world is really messy, and a lot of the problems that we care about are actually hard. So NP completeness is the theory of the hardness of computational problems. And what we'll see is that the theory is kind of about how are different problems related to each other, right? So we'll see that we take one problem and we try to kind of reduce it to another problem. And we're trying to understand the big picture, like how are these problems all related to each other. So we see maybe it's very interesting where you see maybe a problem of checkers or chess, you can reduce it to a graph problem, or like a problem of solving a circuit, right? And that kind of shows the connection. There are a lot of beautiful connections there. It's a very rich theory, but also it's something that's impossible to cover in full detail in one or two classes. So usually there is an independent course on computational complexity where you learn about this stuff. But we'll see how much we can cover in like maybe part of today and next class, and hopefully we can do some interesting stuff. Okay, so today we'll mostly start NP completeness, kind of go through the definitions, try to understand the intuition, and then next class we'll actually do some reductions. And before that, we are going to try to wrap up our discussion of max flow and kind of introduce the algorithm called Dinic's algorithm, which is an improvement over Ford forecasting, which we covered last time. So that's going to be what we are trying to do. But just to connect with last class, let's look at, like, we didn't look at, so last class, we looked at the correctness of the Ford-Fulkerson algorithm, right? And what was the theorem that we proved? Do you remember? So it was the max flow mean cut theorem, right?
Oh, the fact that if there was the three sections to it.
Right.
It was related to the fact that if you had a path going through it, then there was a cut necessarily.
Right. So we know that the Ford-Fulkerson algorithm stops when in the residual graph we have no more SD paths. That's when we stop. We cannot see any more flow. That's part 3 saying that if there are, so what we usually use is that 3 to 1 is saying that if there is no SD path in the residual graph, then we know that at that point in time we have a flow. The value of the flow must equal the capacity of some cut. Okay, but this still does not tell us that it is maximum. We know it's maximum when we say 1 also implies 2, right? Because if this is true, then we know that it is a max flow.
Yeah.
So all these 3 together, starting from 3, prove the correctness of 4%. That at the end, when it terminates with the max flow.
Yeah.
Okay, and then we kind of give a sketch of the proof. And now, but what we didn't talk about is we should talk about the runtime of Ford-Fulkerson. Okay, so let's kind of briefly look at that. So what is the runtime of Ford-Fulkerson? So let's think about that.
Probably related to the overcapacity.
Yes. So let's make an assumption first that the capacities are ints. Okay. Now, if a capacity is an int, then what do we do in the fourth recursion algorithm? We say that kind of while there exists an SD path in G of f is the residual graph, then find an SD path, right? With some bottleneck capacity. So we assume that initially the flow is 0 with bottleneck capacity f prime. What does that mean? That means I found a path, I checked the capacity of the remaining residual capacity of every edge in that path and find the minimum. If the minimum is greater than 0, that means I can still send some flow, right? So that means that this value f prime has to be greater than 0, and then we do f equal to f plus 1. Mathematically, what this means is that f prime is the amount of capacity we are using up on that path. So for every edge on that path, we will increase the capacity by that amount, right? Every other edge stays the same, right? And then eventually, when we return a max flow, we are just going to check like the source and its adjacent edges. What is the flow of that? That's our max capacity. That's the value of the flow, right? So when we return the value, we actually don't just return this flow vector. We just return the sum of the edges that are adjacent to the source. Okay? So that's what we return here. So it doesn't matter, like we can just return the flow vector or we can return those values. It doesn't matter because you can compute the flow, the actual optimal flow value in kind of constant time from the flow vector. You just add up a few edges, the value of a few edges, right? So that basically you can ref f or the value of f, which is summation of all edges SV. Okay. So now how long does this run? What is that complexity of each of these iterations? How much time does it take? Order of E?
Yeah.
Because it's a depth, you can use depth first search, right? To do a search which is order of the number of edges. So
Yeah.
this is going to be this every time to find an SD path you need order of n time, right? And then even this addition is also O of n, because you're adding at most n edges.
Yeah.
Okay, and then now the question is how many times do I need to run this while loop?
And it depends on your capacity of the task.
Right? So in the what would be kind of the worst case number of iterations? So let's say that we kind of know like the value of the flow at the end of this run is kind of V of f, right? Let's assume that that's a variable quantity. And now every time I find an SD path, what is the worst possible SD path I can find?
The one where you only add one permanent.
Exactly, where the bottleneck capacity is 1.
Okay.
Which means that, so V of f is a quantity that I don't know, but I'm assuming that there is going to be some flow value written by 4%, which is a finite quantity. But to reach that, I start with f equal to 0, right? And then if I am unlucky and the first path has bottleneck capacity 1, then the flow can only increase by 1.
Yeah.
So flow goes from f equal to 0 to f equal to 1 up to, and then it's going to terminate when I actually reach the value of the flow that I expect from the algorithm,
Yeah.
which is going to be f equal to V of f. That means this runs time order of the value of the flow.
Okay, so that means my runtime is, it's actually not really a runtime that just depends on the graph parameter. It also depends on the value of the flow, right? So that actually the runtime is m times the value of the flow, right? And then in general, the value of a flow can be extremely large, right? Right? And there is nothing that stops me from doing a value of a flow. I can create a graph where the value of the flow is like 10 to the power n, right? Because it's a variable thing. I can just put in very big capacities such that my value of my flow is very large, which means that that is why this actually is not an exact polynomial time algorithm. So this is usually called weakly polynomial. Because there is a dependence on the flow which can be arbitrarily large, right?
Didn't we have a similar thing with weights?
Exactly. We have to make some assumptions, right?
Yeah, we made the assumption that it's an integer, but
Right.
would it not be weakly polynomial as well?
Right. Which algorithm was that?
The knapsack one?
The knapsack, yes, exactly. Knapsack, in general, the knapsack is actually NP hard, unless you put some extreme restrictions on the capacity of the knapsack. Yeah. So now, like just to look at an example, we want an example where you can actually achieve such a bad runtime. So it's a simple graph that which you can do that, which is, again, it's kind of the same graph that we keep seeing again and again, right? We just have this path here, right? And then here I can put a number b, where b is extremely large. B is like about, let's say, I can do anything, right? I can do 10 to the power 10 to the power 10. No one's stopping me. It's still a constant, but it's an extremely large constant, right? And then if here I have b, here I have a b, and here I have a b, and here I have 1. And then because we are choosing DFS can find any path, right? So what will happen in the first iteration, I am allowed to choose this path, right? And that reduces the residual capacity by just 1. So everything, this gets 1, right? And now at this point, at this point, this edge is reversed, right? I've used the bottleneck capacity, so if you don't have a direction anywhere here, our next direction is this way, up. So that means this becomes 1 by 1, and then I have a path here, and now the only path out of here is this path, right?
Yeah.
And again, this path, the bottleneck capacity is again 1. So now we just do this, and then this gets reversed again, and we keep going on. So we can see that the runtime is just going to be depending on this value b, which is extremely high.
Yeah.
It will take forever to finish, and that's even with integers. If your flows are fractional, then basically it can take infinite time, depending on how you represent a float on the machine, right? So that means float recursion is a good algorithm if we have a kind of a bound on the capacities, but otherwise we need a better algorithm, right? And we'll kind of try to understand how we can improve this algorithm. So there are two ideas. One is about like kind of, it's a very simple idea, kind of using shortest hop paths. And the other idea is about something called a blocking flow. And if you combine these two ideas, we can take Ford Ferguson and improve it and make it like into what is called a strongly polynomial algorithm, where we don't have the dependency on the capacity. Okay. So the idea is so let's first talk about the shortest hop path. So in general, when we try to find an ST path, we use DFS, right? But there is another algorithm that would give us. So DFS is that first search, and there is what is the other algorithm? Whatever similar, it's DFS. And what's the property of DFS? What type of paths do you get with DFS?
You get the shortest path.
The shortest path, not in terms of weight, but in terms of hops.
Yeah.
Right? So that means that if we did DFS to find the ST path here, when we start, we are not going to go this way because this is 3 hops, but we go the upper part, which is 2 hops.
Yeah.
And then we will find the flow of, we'll actually find the flow of the full, we'll find the flow of the full capacity here.
Yeah.
Right?
But we aren't guaranteed that.
Right. Sorry?
We aren't guaranteed that with every graph. We discussed that like last class.
Yes.
Or we can find the path on the best first search.
Right, but that was before we had the issue of we had residual graphs.
Oh, okay, yeah.
So the residual graph where we actually, if we kind of saturate an edge, we go the other way, we reverse it. With that way, we can get out of that.
Yeah, that's true.
Yeah, but it will still take time. And then here we actually do 2 iterations to find the path, right? So shortest hop path actually helps. And that's kind of related to the idea of kind of what is known as Edmonds-Karp algorithm. That's about using the shortest path instead of the any path, right? And now the Edmonds-Karp algorithm is very simple to state that instead of doing DFS, use a DFS for your paths, and that's it. You get very good performance. But the difficulty is actually how do you prove that you actually have improved runtime. So that requires a lot of, and that's a kind of a tricky thing. So for that reason, we'll mostly not just look at it intuitively and not prove it rigorously. It's a very difficult. It's kind of a difficult proof to do. So I won't cover it in much detail. And the other idea is what is known as a blocking flow. Okay, and this is both shortest path, and this is what is used in Dinic as an algorithm. Okay, and that's kind of the algorithm that you are doing in your assignment. So the blocking flow is the construct that is used in Dinic's algorithm. Okay, so let's talk about what is a blocking flow. And the algorithm will be much clearer when you actually go through an example. But I'm going to try to define it first. Okay. Okay. One definition that we're going to need is you say that an edge is saturated when
It is saturated if it has no more capacity left.
exactly. So that means the flow on E is exactly equal to the capacity of E. Okay, it's just a simple definition, but it's useful to know that. Okay. And now, what is a blocking flow? Every ST path, we have a saturated edge. Why is it called blocking? Because if you reach a blocking flow, there is nothing more you can add there. Because there are no more ST paths on which you can send in flow. Because every ST path has a saturated edge, and that saturated edge, what is the residual capacity on the saturated edge? 0. So there is no way to, basically if you look at any path, right, the saturated edge would have capacity 0, so the mean capacity on that path is 0, so you cannot add anymore. So once you reach a blocking flow, once you reach a flow that is blocking, that's the maximum flow you can add. Okay? And now this blocking flow is actually, we get the blocking flow. If you remember, before we did Ford Ferguson, we tried a greedy algorithm. Right? What was the greedy algorithm? We just tried to find an ST path and add flow, as much flow as I can. But we didn't have any reversal.
Yeah.
So when you finish that greedy algorithm, what you end up with is actually a blocking flow. Okay? So again, it's going to get clear with an example. So again, we just look at one of our popular graphs. Right? Right? So again, if we run through this path, right? After you run through this path, you have capacity 1 here, capacity 1 used up here, and 1 used up here, right? And then at this point, this is without any reversals. The other path does not. The other path is like this one, and then there are no more ST paths, right? Everything is saturated.
Yeah.
So that's a blocking flow, right? And then a blocking flow does not mean it's going to be optimal. A blocking flow is because we are just greedily adding flows until we cannot do anything else, right? So the blocking flow is not optimal, but the idea of blocking flow is that the blocking flow is kind of a building block that we use to make flow computation faster. Why? Because when we are doing blocking flow, we are trying to push as much flow as possible in one go. In the previous algorithm, in Ford Ferguson, we just find one path where we cannot add flows. And in a blocking flow, we can actually find multiple paths on which we can send a flow. And in that way, we kind of doing a lot of computation in a shorter amount of time by using a blocking flow. Okay? So that's the idea. Right? So the greedy algorithm that we saw before Ford Ferguson doesn't return an optimal flow, but returns a blocking flow. Okay? Right? So now let's, so greedy algorithm returns a blocking flow. So now if we have to compute a blocking flow, right, what is the maximum time it would require to compute a blocking flow?
Well, maximally you just visit every edge once.
Mm-hmm.
So maximum is depending on the number of edges.
Yes, that's true. So in a blocking flow, if you are using like the greedy algorithm, right? The greedy is trying to find one path, right? And in one path, it can saturate at most one edge, right? Because if you think like this, right? So it's like 2, 7, 11, 2, 13, 1, right? My greedy algorithm is going to try to find one path. It doesn't. So the blocking flow is a combination of paths, but to compute that we find one path at a time.
Okay.
Right? So I might find this path, right, and then I saturate this edge.
Okay.
So this is no longer in the picture. So now the remaining flow here is 2, this is 2, right? And then the next time I run it, I'm going to try this flow, and then I'm going to saturate one of this, right? And then next time I'm going to run this, I'm going to saturate one of this, right? So the total number every time I find a path, finding that path takes order of m time, right? And then if I have n edges total in one path computation, once I find the path, I can only saturate at most one edge. So I would, at the end of the iteration, I still have n minus 1 edges that can be saturated. So in the worst case, it's m times m. So you can do this in order of m squared. That's the time it takes to compute one blocking flow in the worst case, right? But now this is because we are doing a naive algorithm. Maybe there are actually techniques to make it faster, right? And I won't discuss that. But there is a way to, if you are kind of careful, you can do this in O of m. Okay, but that gets a bit complicated, and that's not the main idea we want to discuss here. Okay, so let's actually write down Dinic's algorithm, and then we are going to do a simulation to understand how it works. Okay. Dinic's algorithm. Again, we start with the flow equal to 0, and then we repeat these steps. So we are going to compute a residual graph. Okay. So GF is the residual graph with respect to the flow F. Right. What this means is that we basically take the original graph, and then with respect to the flow F, we compute the residual graph. We know how to do that, right? We compute the remaining capacity, right? And if whatever capacity the flow is going through, we add the reverse edge correspondingly, right? And if the remaining flow becomes 0, we don't have the forward edge anymore. That's the computation. We know how to do that. Okay, but that's step 1. And now next is kind of an unintuitive thing that we do here, and this is where we are going to use the shortest paths, the shortest hop paths. Okay, what we're going to do is we're going to construct another graph called G prime, which is going to have the same number of vertices but a different number of edges, right? And now these edges are going to be a subset of the original edges, and these are going to be only edges in ST shortest paths. Okay, what does this mean? We'll look at an example, but this is the shortest hop paths. Yeah, here in flow, shortest always means shortest hop paths. What we're going to do is that we have from S to 2 we have a lot of paths, right? But for every such path, we are only going to keep the shortest hop paths. Okay, and then once we find that, so I'll do an example to explain it better, and then we're going to compute something. F prime is going to be a blocking flow in G prime, right? So G prime itself is a graph which has a smaller number of edges because we're only keeping edges in the shortest paths, shortest hop paths. But on that graph we have edges with residual capacities. So on that we can compute a blocking flow using the greedy idea. And we're just going to find the path in O of n time, and then find
the bottleneck capacity and keep doing that until we cannot add any more flow.
Okay.
So this is a difference from for person where every time we are computing a flow, we just find one path and find the flow along that path. But here, at every step, we are finding this blocking flow, which is kind of, in some sense, an aggregation of paths. It's not flow along just one path, but it's flow along multiple paths. We keep adding flows until we cannot add anything else in the graph anymore.
Okay.
That's the blocking flow, and we're going to add that to our flow.
That's pretty expensive, right?
We'll see that this actually speeds up, because what is the problem with for person? Right, each individual iteration is fast, but we have too many iterations.
Right.
So basically, we are batching these into smaller steps. So each internal step now takes m square time, which is the polynomial.
Yeah.
But that would make sure that the full iteration doesn't take infinite time.
Excellent.
So it seems a bit unintuitive, but we'll see that it actually helps to speed up things.
Okay.
Right? And then we do f equal to f plus f prime, right? And here this is basically an edge-wise addition, and this f prime gets added to only edges that are included in the blocking flow, which is a number of different paths, but there are other parts that are not used here. Okay? And we repeat until we get f prime equal to 0, which means that we repeat until a point where f prime 0 means that I could not find any more blocking flows in the remaining graph, because there are no more ST paths with unsaturated capacitors. That's what we know. The primary condition is similar to 4%, but we'll see that this actually drastically speeds up the computation. Okay. All right. So I think an example is going to make it clearer what's happening here. Okay. So let's start with the graph here. Okay, so now this is our initial graph, and initially the flow is 0, so this is my residual graph, right? And then what do? In the residual graph we find only the ST shortest paths, okay? And now from S to T, what is the shortest hop path from S to T?
The top and bottom paths.
The top path, right? So this is the shortest path. This is 3 hops. There is no more than. And now there is another shortest hop path, which is the bottom one, right? So we can consider both of those. So now this graph has these 2 shortest ST paths with 3 hops. Now there are other paths here, right? From S to T, this one, this one, this one, this one, right? So this is this way, but that is how many hops? 1, 2, 3, 4. So it's not the shortest hop path. So we're going to ignore it in this iteration. Right? And similarly, we have 1, 2, 3, 4, 1, 2, 3, 4. I think those are the, but those paths are 4 hop, so we are going to ignore them. And now my graph, the subgraph that we are considering, where we are looking at E prime as a number of subset of edges, is basically these edges. This edge, this edge, this edge, this edge, this edge, and this edge. Right? Every other edge we are ignoring. And now we're going to try to do a blocking flow on these 2 paths, right? So if you do a blocking flow, what do we get? So basically now we're going to say that the minimum distance in G of S from S to T here, what is the minimum hop distance here?
What is GTM here?
So G of F is the residual
G of
graph.
F. Okay.
And from S to T, what is the shortest hop path? That's what I'm doing in my G of S.
I see.
here, what is the current shortest hop path length?
20.
No, hop, number of hops.
Oh, sorry,
Three. We're keeping track of that.
right? So we're just going to keep track of that. And now, in this graph, I'm going to just do blocking flow. Blocking flow means I keep trying to find a path and kind of using that, right? So I will first do this path, and I see that the residual capacity, the blocking, the bottleneck capacity is 5, so I'm going to send flow 5 along this path, right? So that means so if I do that, then what I'm doing is I'm sending 5 along here, 5 along here, and 5 along here, right? And then, so that's one iteration of the blocking flow computation. And now I can send, the bottom path has bottleneck 6, so I can send 6 flow along the blocking path, right? And now after this graph, right? So now my flow so far is, I've sent like kind of 5 plus 6 equal to 11 across these two paths, right? So I keep track of that, right? And now at this point, we cannot do anymore, so we're going to go back to our next iteration. So for that, at this point, I'm going to do the residual graph computation, right? So what would be the residual graph at this point? Right? So on the top path, I still have 5 along this way. I'm going to do a reverse 5, right? So it's going to be 5 this way and 5 this way. For the top one, just a reverse edge because there is no more capacity left, right? And then this one also, just reverse, no more capacity left. This one will have forward remaining 2 and backward 6. This one just a reverse of 6, and this one will have forward 5, and remaining is going to be 6. And then the remaining things we didn't use, right? So it's going to still have here, it's going to be 15. This is 5. This still is 4. This still is 2. And this still is 10. Right? Okay? Is this okay so far?
That's right.
Okay. And now on this new graph, again, I'm going to do the same thing. I'm going to try to find the shortest hop paths from S to P. Okay? So now, the previous path that I used is no longer available. Okay? So that was hop 3. So what do you expect then the next shortest hop paths you will have?
4.
It's going to be 4, right? Because you see that we've kind of used up all the shortest hop paths. So those paths are no longer available. Because once you saturate an edge on that path, at least one edge reverses. So that path has a reverse edge, so you can't go from S to P anymore.
Okay.
So now here we have this path, this path, this path, no. But here you can go from here, 1, 2, 3, 4. That's the shortest hop path.
Yeah,
Or you can,
symmetrical.
right. And then, like, you're not going to try to go back here because that's just going to increase your hop count. That doesn't make sense.
Our assignment, do we get a BFS that rate checks for cycles, or do we have to write that ourselves?
You have to. If you do a BFS, right, you're going to find the shortest hop paths.
Oh, yeah, you
Yeah.
have to check for cycles, it checks for
Yeah.
cycles.
Yeah. Because it's the shortest hop, so you will never get into a cycle.
Okay, you're right.
Yeah. And then from S, you just have to, you break when you find P in your hop count, right? But now let's try to find the shortest hop paths in here. So we have like this one, which goes from here, right, and then it goes here, right? And then it goes here and here, so that's distance 4. And there is another path which is this one, right? So maybe we should change color. This one, this way, and this way, right? So 2 shortest hop paths, and then the remaining paths you can check that they are going to be higher hop. So at this point,
There's 2 more that's also 4.
2 more,
Yeah, you don't have to go down 10, you can go up 4.
but then from 4,
The
This
5
is
is
reversed.
reversed.
So you have to go there.
so at this point, now at this point in the residual graph, your distance between S and T, the shortest hop is 4 now. Okay, so now you can see at every iteration we take m square time to find the blocking flow, and at every iteration the shortest distance from S to T is increasing by at least 1. Now what is the maximum distance between S and T that you can ever have in a graph? Like what is the maximum path length that you can ever have in a graph without cycles?
The maximum is 10.
The maximum number of edges you can have in any path, in any simple path in a graph, ST path.
The number of edges along the same path.
Yes, that's true, but in terms of vertices, what is the maximum?
Also the number of total vertices.
Well, if I have a graph like this, right? The number of, so this can be like even more complicated, right? The maximum path between, so if you have, basically if you have a path with more than n edges, what happens on that path?
It's reached a cycle because it's hit the same node twice.
It's the same node twice, so it's going to have a cycle.
Right.
So, but if you want to find the shortest hop path, the shortest hop path will never have a cycle.
Right.
So the maximum shortest hop path that you can ever have in a graph is n minus 1. Right. So that means if you start with distance 0, then if the shortest distance starts with 1, then the shortest distance in every iteration increases by at least 1, then how many iterations can you have at most? At most n. Because every time shortest distance, as we saw here, again this requires a proof, but we are not going to do that proof, it's complicated. In the first iteration, we got from 3 to 4. The next iteration is going to be 4 to 5. And how much can this increase this shortest distance? Up to the number of vertices. So that means the total number of time we run this outer iteration is at most 4n. And we take each iteration, we take m squared out. So total runtime is order of
n by m squared.
n times n squared. Number of vertices and number of edges squared. So now in this runtime we don't have the flow value. So now we actually have a strongly polynomial algorithm. Okay. But let's we're gonna specify that. But let me just kind of finish through this example. So now at this point we have. So we are just going to use these two paths and then find flows along them. So right, what is going to happen? On the top path we have 5, 15, 10, and then 5, right?
Yeah.
So we are going to do 5 along here, 5 along here, 5 along here, and 5 along here, right?
Right.
I think somewhere
Did we make a mistake?
yeah, let's see. Not a mistake, but basically what we're going to do is that we need to find a blocking flow, So now we have two paths that share some edges. So we need to kind of be cooperative here. And then what you can see is that what you're going to do is that in the top path we send around 3 here, 3 here, 3 here, and then 3 here, and along the bottom path we send 2 here, 2 here, and then that 2 plus 3 gets added to 5 here on this path. This is the shared path, 3 plus 2, and then again here also 3 plus 2, right? So that means the total, that's how we're gonna find the blocking flow. Okay, and now if we do that after the final augmentation, right?
This requires us to sort all the paths by their bottleneck, minimum bottleneck first.
Yeah. You don't have to sort. If you just do at that point to find the bottleneck path, to find the blocking flow, you don't have to use shortest path anymore. You can just use any path there. Right? So that does not require shortest path.
It doesn't require shortest path because they're all the same length, so all the same amount of pops. But we just shared it. The reason that we shared it is because we found out that 2 is the smallest.
Right.
Smallest bottleneck, sorry. And then we subtracted that from that entire path. And then we went with the 5 one. We found out 5 is not is too much, so we just had to do 3 on the top one.
Right. It would not matter. I'm just for this example I'm
For this
showing that.
example, okay.
But I can also saturate using the first path,
Mhm.
and then after that they won't be this path is going to be blocked,
Right.
so that I won't have any more paths.
Got it. Okay.
So the shortest path would still increase, and you will be sending the same amount of flow,
I see what you mean.
right? So here the total bottleneck flow you're sending eventually is 5, right?
Yeah,
And I
yeah.
can just use the first path to send 5 in,
Yeah. Okay.
right? So that's the idea. But I just for sake of my example I did that.
Okay.
But at this point, so now what is going to happen to the new, at this point we did the blocking flow, and now we're going to compute the residual graph again, right? So what is going to happen? So if you now look here, the top path we again send 3 flow, and we previously had 5 from the reverse. So now the reverse is going to be 3 plus 5 equal to 8, and the top is going to be just 2.
Right.
Remaining. Right? So this is going to be 2, and this is going to be 8, right? And then the bottom, the bottom is fully saturated, right? Just 8 in the reverse direction. Okay, and then this one is staying the same. We have this one. So on this path, we're going to forward. We still have 12, and backward we have 3, right? And on this path we just have backward 2 because it's saturated. And then on this path, on the forward we have I think 7. 3 plus 2 equal to 5. So forward still have 5 left, and backward we have new 5, right? And this stays the same. And then
Oh,
6, we used the 5 again, and previously we had 6, so just 11 in the reverse. 11 in the reverse, and then this is, we didn't use, this is still 4, and then this was 5. Okay, and now if you check here, there is if you want to go from S to T, you can check T here, right? So T, both edges from T are outgoing. There are no ingoing edges into T.
So that tells that there is no more paths from S to T. Because whatever you do, you reach here or here, from there you can never get to T.
What's the formal way of discovering that without looking at two? We run up
Just run your, so at this point, we found the residual graph, and you're going to find the next shortest hop path.
Okay.
And then you won't find any because there is no path.
Right.
So
And
your
BFS
graph
will terminate when it goes on its 10th cycle.
Right. But this terminates even before that.
Even
There is
before
no
that.
path. But in the worst case, it would go up to n-1 iterations.
Right? So now at this point we actually terminated, there are no more outer iterations, so actually our, we finished when, at this point there are no more ST paths. So it's going to be a max flow.
And again, how do we guarantee this is a max flow? So this is a situation where there are no more ST paths in the graph.
Yeah.
So you now apply the max from theorem again.
Right.
It says that if a graph has no, if a residual graph has no ST paths, that means there is a max cut, there is a mean cut, there is a cut that matches the flow value, and if a flow value matches a cut, that has to be the max flow. So again, to apply the theorem, you just need to find a residual graph that has no ST path. It doesn't matter how we got there. We got there quicker because we did some smart things. But once you get to the state where there is no ST path in the residual graph, you immediately apply maximum cut theorem, and you can guarantee that it's going to be max flow. So the correctness is already we did the correctness. We just reuse it. We just now speed it up. Okay? And then what is the runtime here? Right. Runtime is order of n times m squared. And this assumes that we know how to prove that at every iteration the shortest hop path, the shortest hop ST path increases by at least 1. We didn't prove that, but we are assuming that. We just prove by picture that it looks like it's increasing, but there is a formal way of proving it, and it's a bit involved, which is why I'm not going to go through it. But if you're interested, please look at the textbook; you'll find it.
Okay.
But I won't like quiz you on that like a proof.
That would be a very
That will be very
final
torturous.
exam question.
Yeah. Okay. Now this is your final algorithm that you can use to using mass. So there are some steps, but I think it's feasible to implement.
Yeah,
Okay.
there's a lot of moving parts.
Moving parts, so you need to kind of modularize it properly. I think.
Yeah.
Yeah. Okay. All right. So actually, that's the end of the discussion of max flow. So let's take a 5-minute break, and then we'll talk about anti-completeness. All right. I forgot to unpause it.
People on YouTube are going to be very confused.
Yeah. Okay. A problem is in NP. If we can solve it in polynomial time on a non-deterministic machine, which is typically a Turing machine. Okay, but what does non-determinism mean here? So a non-deterministic machine, or we can say a non-deterministic kind of algorithm or program. Right, so you can write a program that is a non-deterministic program. What does non-determinism mean here? It means that at every point of your program where you make a decision, so if it's what is a deterministic program, A deterministic program means that at every point you just take one step and it's fixed what step you take, right?
Yeah.
Whereas a non-deterministic program means that at every point in your program you have multiple choices, right? So basically it's like this is your time, and here you can have like a number of paths you can take, right? And these are all possible choices. And then once you take a choice, you again have a bunch of choices. So you kind of
trying to prove fate's existence,
yeah,
trying to solve easy probability.
right, exactly. But every point you have a lot of choices, right? And then you say that you can solve the problem with this non-deterministic machine if there is just at least one set of choices that leads to the correct answer, right? So, and then a problem is if you can do that in polynomial time on such a machine that can allow you to simulate all these paths in parallel, then you have then the problem is in NP. Okay? And now, if you actually need to do this in a finite machine, right? The only way you can do it is you can actually simulate this by running all these things in parallel, right? But as your branching factor increases, at one point it becomes like physically impossible because there are so many possibilities, right? But the idea is that if there was this imaginary machine where you can basically test all possible paths in parallel, and then if you can do that in polynomial time, then the problem is an NP. Okay? That's the idea, but we'll look at some examples. So the example that I want to talk about is the satisfiability problem. In this case, we're going to have a 3 set. Okay, what is the problem? So I have what are called as clauses. Okay, I have m such clauses, and each clause has 3 variables. Right? I have n variables. Okay, each variable can take either the value true or false, or 0 or 1. Okay, so an example can be something like this. Okay, so an example can be I have x, right? I'm going to say plus, okay, x plus y plus c bar, okay, and then I'm going to say x plus z plus u bar. Okay, so now x, y, z, these are my variables. I have n of them.
Okay.
So what does this mean? So basically I have this, and these are like, in this case we have 2 clauses, but I have m clauses in general, right? I'm going to have m clauses, and the variable x can take the value 0 or 1, true or false. Similarly, all the variables, so it's like x1 up to xn, all of them can be 0 or 1. And now the question is there an assignment of 0 or 1 to all the variables that satisfies all these clauses?
What's the operation between them?
So this plus means OR.
Okay.
So if this is false and true, this means that at least one of these must be true. And this means that this is an AND operation.
Okay.
I need all these clauses to be satisfied for true. So depending on how I assign 0 or 1 or true or false to these variables, I might get that all of these clauses together give me true or false. So again, it's a decision problem, right? And now, if I think about a naive algorithm, what would an I algorithm try to do?
Just run through all possibilities,
Right.
permutations of the variables.
How many do I have?
M to the power of m.
2 to the power n combinations, right? And then for every combination, I have to check these m clauses, right?
Yeah.
So
Big
that
pi.
is like each clause has 3 variables,
Mhm.
so 3m combinations.
Yeah.
So the total runtime is 3 to the power n. So in general, this is an exponential algorithm.
Yeah.
So that's a naive exponential algorithm. But now let's say I try to run this on a non-deterministic, using a non-deterministic program where I can check things in parallel.
Mhm.
So what would I do here? What can I do here? Let's say we have an imaginary machine that can allows me to check all paths in parallel.
Okay.
So how many paths do I have here?
You have n paths.
By path mean like all possible combination of variable assignments.
So then
2 to the power n.
Okay.
So 2 to the power n paths can be run in parallel
Mhm.
on a non-deterministic Turing machine. And then if at least one of these paths gives me true, then I know that I have the answer, because I'm looking for just one satisfying assignment.
Mhm.
So if I have a non-deterministic machine or a program, if all those things can be run in parallel, that means that all of them, every path takes, each path takes how much time?
Each path takes 3m time.
Each path takes 3m time, and now I'm not running these paths in parallel, in sequence, I'm running them in parallel.
Mhm.
So the time for all these paths simultaneously on this parallel machine is still going to be 3m.
Mhm.
So on a non-deterministic machine or a Turing machine, the complexity is going, the time is going to be 3 of m, which is polynomial.
The Turing machine not deterministic.
The Turing machine can be deterministic or non-deterministic.
Same, sure.
Yeah, but the non-deterministic Turing machine is more powerful. So that means that now that means this problem, if I have this crazy parallel machine where I can run all these paths in parallel, then on that machine I can check this, I can solve this problem in polynomial time. So that means this 3 sat is in NP. Okay? So that's the rigorous definition of NP. If you allow to check all possible combinations of your input in parallel, and you can check all paths, and on just one path you need to find a solution. If you can do that in polynomial time, which happens in this case, that means that problem is in NP.
Mhm.
And now there is an alternative definition, is that, so now what we have here is that we have, like, for example, we have this, like in this case for 3 set we have this 2 to the power n possible paths, right?
Yeah.
So in this like crazy parallel machine, I would kind of invoke all these paths in parallel, and the first one that tells me that there is an answer, then I'm done, right? So I don't have to waste exponential time for all these paths. Now the other way to think about this is that, okay, each of these paths represent one possible combination of the inputs, like one possible assignment of variables, right? If I give you one such possible assignment, how long does it take to check whether that assignment gives you the correct answer or not? 3m, right? So that means if I give you a guess, if I guess an answer, right, what can be a guess? I can say, okay, I guess that x1 is 0, I guess that x2 is 1, I guess that x3 is 0, and so on, and let's say that xn is 1. That's one possible combination from the 2 to the power n combinations. And I just want to check whether does this satisfy the formula or not. So if I give you this possible input, how long does it take to check whether this is a valid input or not? 3m. Again, so that's polynomial time. So given an input, I can check whether this is a correct solution in polynomial time.
Yeah.
And that's the alternative definition of NP. I can, given a possible solution, you can check or verify whether your answer is correct, right? In NP, right? So in general, checking is, if you can, the task of checking a problem is easier than actually solving it, right? So like if someone gives me a solution to a hard problem, like coming up with a solution is harder, but if I have to just verify that, that's usually much easier. I just see if it's correct, right? Right, so it's easier to do it. So even if it's a hard problem, finding the solution is hard, but once the solution is done, checking it is easier. So that's kind of the idea, that if you can at least check the problem in polynomial time, then it's a NP. But that doesn't mean you can solve it in polynomial time. Okay? So just to give an example, right? So so we said that 3 coloring is NP hard, right? But so finding a possible 3 coloring is hard because there are a lot of combinations. But if I give you a graph and I give you an assignment of them, basically I give you, right? I say that I color this black, I color this black, I color this R, I color this R. I can just run through every edge and check whether the vertices of that edge are the same color. So I can check in order of m time. I can check whether this is valid coloring or not.
Right.
So that means coloring is an NP, right? So like 3 coloring. Right? And we also show that 3 sat is an NP, right? We just argued that. Okay. So that's the definition of NP. Any questions about that?
Seems like this definition is to figure out if your problem is even harder than NP. So if finding a valid solution in itself is an NP problem, it can't be solved in polynomial time.
Right.
Then you have a question that's even harder than NP.
Right. So that's kind of the. So now we know that what is NP, and then the other question is like, what do we mean by NP complete problems? That's the next question. Like, why do we say, when do we say a problem is NP complete? Right? And the answer is 1, like we ask the problem X is NP complete if the problem itself is in the set NP, which means that the problem can be checked in polynomial time. So a tentative solution can be verified in polynomial time.
Right.
And the other thing is that for any problem y in NP, right? So that the class NP possibly has a lot of problems.
Yeah.
If you take any such problem, then there is an efficient reduction from y to x. By reduction I mean I take an instance of any problem y, and I can convert it into an instance of problem x. Right? And now what are the implications of this? right? So let's assume that let X have a polytime solution, right? If X has a polytime solution and I know that X is NP complete, that means that if I take any problem Y in the set of NP, I also now have a polynomial algorithm for Y. How? Because I know there is a reduction from Y to X, right? I take an input for Y, I pass it to Y, and then what do? I just convert the problem, the input for Y into an input for X, and I know that X has a polynomial solution. So if I combine the reduction from Y to X and the polynomial time algorithm for X, now I have a polynomial algorithm for Y. So if that means that if any problem X in NP has a polytime solution, then all problems in NP are NP, which means that actually P and NP become the same. Okay?
So that's the implication of this. In some sense, once you prove that a problem is NP complete, it means, so when you have this reduction, that means that X is at least as hard as any other problem in NP. Because if you can solve X in polynomial time, every other problem is solvable.
Does this reduction go backwards?
No,
Okay.
it only goes this way. That's always the operational reduction. So it's a one-way reduction. And this arrow says that X is at least harder than Y.
Right.
That's the idea. So does that make sense? That's kind of a key idea. Why is it called harder?
X is harder than Y.
Because to break, if X is not harder than Y, then, but in some sense that's the definition of the hardness relation, right? That if you can reduce Y to X, that means X is at least as hard as Y.
At least as hard.
At least as hard as Y.
Yeah.
Right? So that's kind of the idea. So once you do this reduction, you are adding a harder problem to your set of problems.
Has there ever been someone that came up with a solution to an NP and solved an NP, but there's no like other NP problems that can be reduced down to it? So you just kind of like found a P solution for an NP problem.
If you find a P solution that proves NP equal to NP, so no one has done it yet.
Well, how would that be equivalent? Like say you found like a problem Z, it's non-reducible to anything in NP. Oh, but then it's not an NP problem.
Yeah.
Okay.
So,
Yeah, so I think let's end to them. We'll continue next time. Next time we're going to kind of review this, and then we're going to actually start seeing how we actually do these reductions, right? And then one thing is that when you say you want to do this reduction, like there has to be like a first problem that is kind of NP complete, right? Because to do this, you need to reduce. You need to basically this. So this actually is for the reduction has to be for any NP complete problem, not just NP. Okay. For any problem that is already NP complete, we need to reduce that to X to prove that X is NP complete. Okay. So that's it has to be in NP, but the reduction from Y to X has to be for all Y that is already NP complete. So that means that we need to first find at least first problem that by itself is NPC,
Okay.
because then to prove another problem X, it has to have a reduction from at least one more problem Y. So there is this bootstrap problem where you need to find this first problem that is actually NP complete. And that first problem was proved NP complete by two scientists called Cook and Levin. So they found two problems that they proved are NP complete. Right? So for that is like a complex proof that required proving that basically you can take any program, any computer program, and that can be mapped to like this three set problem. So the program, the idea is that the program, they show that the program runs on a Turing machine if and only if there is an equivalent representation of a SAT formula that is satisfiable. So you kind of find this reduction, and it's a very complex thing, but that proves that 3SAT is NP complete. And now in your set of NP complete problems, you have 3SAT, right? They did the hard work. Now all you have to do to prove a new problem is NP complete is show that it's an NP, which is really easy. You just have to see that the checking the solution is in polynomial time.
Right.
But then you just have to take your new problem, and then 3SAT is already NPC.
Okay.
You take 3SAT and reduce an instance of 3SAT to an instance of your problem in polynomial time, and then you prove your new problem is NPC.
I see.
And for the longest time, that's how people would write new papers. You take a new problem, and it's from 3SAT, right? So what is happening is that an NPC is a set of problems, right?
Right.
So what Cook did, it said that 3SAT, he proved the hard theorem that 3SAT is in NPC. And now let's say you come up with a new problem, like let's problem X. So what you need to do the problem X is in NP, and then the set NPC only has 3SAT now. So all you have to do is you have to find a polynomial reduction from an instance of 3SAT to an instance of X. And if you can find the polynomial and reduction, then X gets added to this set of NPC problems. Right, so 3SAT is there, and now X is there, right?
Yeah.
And now if I have another problem, I can reduce from X to that problem, and I can prove it NP complete, right?
So what did Cook do to prove that it was NP complete over just being NP?
That's the hard part. He basically showed that the 3SAT is equivalent to running any arbitrary program that can run on a Turing machine. That program has an equivalent circuit representation. So that's how he proved that it's an NP complete problem.
Okay.
Right?
I'm a little lost on what specifically is the difference between NP complete and NP, because it sounds like from your description, like the way that they prove that 3SAT is NP complete is the way I would prove that it's NP, but clearly I'm missing
No,
something.
that's that if you can to prove NP for 3SAT is means you check solution in
Yeah.
polynomial time.
Right.
But NPC means that I need to find a representation. So the representation is for any arbitrary program, which can be extremely complex. Whatever program you have, if that program runs on a Turing machine, that means that that program has an equivalent representation in a circuit, which is a 3SAT circuit.
Okay.
Right? So anything in the world that you can compute on a Turing machine, you can, if that program is computable, it's also satisfiable in a formula. You can find a formula representation for any program. So that proves that 3SAT is NP complete.
And what's the usefulness for knowing that 3SAT is it can be represented as a formula?
3SAT is a formula representation.
Right. Okay.
So
Okay.
that's your bootstrap program. And now if you want to prove anything else NP complete, you just use 3SAT.
Okay.
And once X is there, if X is a simpler problem to use, next I say I want to prove that Y is NP complete, I do the same thing. I just show that Y is an NP, and then I can just use X to find the relation of X to Y.
Or you can do 3SAT.
You can 3SAT, but maybe 3SAT is harder because I need to find a a input of 3 set and mapping to an input of y.
Right.
So if I find that finding an input of x and that and reducing the input of y is easier, I would use that. Because I just need to use it one of them. Because once it's in there, they're all kind of, you can use any of them.
Yeah.
So we'll get into more detail next class. I think we are out of time today, but we'll continue this. Okay? Thank you.